start that up. All right. It's pre-calculus time. Sorry, I am very tired today because my young son decided he did not want to go to sleep last night. Let's put it this way. I wanted to be in bed by 10. I was finally able to get him asleep and in his own bed at 1:15. So that's like, and then I have to get him early to come here. So yeah.
Come here. Wait, what? Do you not live on campus?
I do.
Okay. What do you mean? You just had a 8 o'clock class?
Yeah.
Okay.
So I'm gonna have to get up and take a shower and get ready, all that stuff. So it's never very fun. All right. So what I want to do first is let's just make sure we got everything with the homework. There was a lot of it assigned last night. If you did it all, power to you. If you didn't do it all, whatever. It's not the end of the world. A lot of it too, though, is just to make sure you know how it all works. Okay. If there's any specific questions about anything you want to see, we can go over it. But a lot of it is just the reason. There's a lot of it, but a lot of it could be done very quickly because it's just a matter of do a conversion or add this or subtract that. So, all right, I see several hands up. So let's go, George. Start with you.
57.
57.
Yeah, I had problems with that one too.
All right. So 57. We're going to convert. Okay. Convert from radians to degrees. Okay? And so we've got, with 57 here, we've got -2 radians. Okay? Well, -2 radians is it's just -2. So what you do here is to convert it into degrees, you just do the usual. It's going to be 180 divided by pi. That's what you're going to times this by. So -2 times 180 over pi, which gives me -360 over pi degrees. And that would be your answer. Okay? That's it. You're not, you don't want to do anything else to this. I think the book is assuming you're actually going to divide that by pi. Don't do that. Leave pi as pi. Okay? So that would make this, if you divide it by pi, it'd be a little bit less than 120 degrees. Negative 120, so it'd be like negative 117 or something like that. Okay? But we don't want to, since we don't want to actually divide by pi, we'll just let this be. So that would be my answer. Okay? If I wanted this in terms of, if I wanted this between 0 and 360 instead of being less than 0, which it currently is, negative pi over 360 again is less than 0. I would add 360 to it. Okay? And so the coterminal angle, the same position, would be 360 minus 360 degrees over pi. And that's really all you could do. You can't really take that any further. Okay? Again, because of that pi. All right? It's roughly equal to, it's a little bit bigger than 240 degrees. So like maybe like 242, 243, somewhere around there. Okay? But again, we don't need to do anything else but this. Okay? So that would be all how you would handle 57. Okay? Any questions? So it ended up being a lot easier than it appeared, right?
Yes,
Yeah. And that's going to be the case with a lot of these problems.
So number 5.
Number 5. So number 5, we got determine the quadrant in which each angle lies. The angle measurement is given in radians. So -1 in radians. Okay. We go ahead and do this. Okay. So here's a 5. Okay. Where the major locations are on here, we're going to see this again after we're done going over this homework. That's 0, okay, this is pi over 2, okay, which is roughly equal to 1.6, okay. This would be pi, which of course, as everyone knows, is roughly equal to 3.14, okay. And this one down here is going to be 3 pi over 2, which is approximately equal to it's 9 divided by 2. It's roughly, it's like about 4.6-ish. Okay. All right. This is minus 1, which means we're starting at 0, and we're going in this direction for whatever minus 1 radians is. Okay. So minus 1 is less than 1.6, right? Okay. Which means I'm not going to quite make it over here to 3 pi over 2. I'm going to end up in this quadrant somewhere. So what quadrant is this? It's the 4th quadrant. So negative 1 radians is in the 4th quadrant.
Oh, okay. So
Okay, that's really all there is to it. Okay. Everyone see that?
Yes, sir.
Okay. And so you could go through like that with all of them. Minus 2. Minus 2 is a little bit bigger than 1.6, so it would be in the 3rd quadrant. Be down over in here. Okay. Everyone see that?
Would they, so how did you know that it started at 0? Do they all start at 0?
They all start at 0.
Okay, got you.
Okay. You always start, like the starting location for all this, and again, we're going to see this today because we're going to be playing around with it as we do the unit circle. The starting location is always right there on the x-axis, okay? And you normally measure things counterclockwise from there. So that's what you go around. That's the positive direction, and this right here is the negative direction, okay? So when you get like negative 3 pi over 2, okay, you're going this direction until you get 3 pi over 2 in the negative direction, which is the same thing as pi over 2, so you'd end up in the same location, okay? Any questions? All right, good. Any other questions? As far as like the mechanics of like changing one thing to another, or calculating a coterminal angle, or finding supplement or complement, are there any issues there?
We do one of those coterminal.
Yeah. So, like number 11, determine 2 coterminal angles in radian measure, one positive, one negative, for each of the angles. There are many correct answers. So, a coterminal angle is basically an angle in the same position, but you've gone around the circle once, or you've gone around it the other way once, or multiple times. It doesn't have to be just one. So, with number 11 here, oops. Okay. Go away. Stop it. Okay. No. With number 11, A, I'm going to just do A because basically A and B just means they split. They just added 2 problems called 11. We're right there at pi over 6. Okay. If I want to find a positive coterminal angle, I'm going to add 2 pi to it. Okay. Because what that's going to do means I'll go around from pi over 6 one whole rotation to get back to where I started. So it's pi over 6 plus 2 pi. It's going to be what?
13.
13 pi over 6. Okay? That's one coterminal. Another way I could find the coterminal, because I want one that's negative, would be to subtract 2 pi. Okay? Which means I would start at the same location and go around the other direction until I made it back to where pi over 6 is. So pi over 6 minus 2 pi is going to be what? Negative 7 pi over 6. Okay. No. Sorry. Negative 11 pi over 6. Excuse me. Okay. Right there. All right. And so there's your answer. Okay. That's how you find coterminal angles. So anytime you have to find a coterminal angle, you're going to, if you're in radians, you're going to add or subtract 2 pi. If you're in degrees, you're going to add or subtract 360. That's it. Okay. The coterminal angle is just the same angle, same position. Yeah.
How do you do number 19?
Number 19. Okay. Find if possible the complement and supplement of the angle. Okay. They didn't tell you this, but you're assuming 1 there is in radians. Okay. It's probably not in degrees. That'd be a little easy if it's in degrees. Okay. Remember, complement
Up to 9.
mean they add to a right angle, which in radians is pi over 2. Okay? Okay. Supplement, oh probably spelling supplement wrong. Yeah, it's two P's. Okay, means they add basically the two right angles, or they add to a straight line. And in this case, that's going to be add to pi. Okay, so to find the angle that's complement or supplement, the complement and supplement with 1. So for the complement, it's going to be pi over 2 minus 1. And for the supplement, it's going to be pi minus 1. And so this one's going to be roughly equal to about 0.6, and this one's going to be roughly equal to 2.14. Okay? And there you have it. Okay?
I thought it was in degrees. I thought it was in degrees. That's
Well,
what-
if it's in degrees, that's even easier.
yeah.
It'd be 90 minus 1, which
The
is
answer didn't match.
89.
The answer didn't match the back of the book, so I was
So.
confused.
There you go. Okay. If your supplement, it's 180 minus 1, so 170. Okay. Yeah. They should have mentioned that you're in radians there. Okay. And that's one thing you do have to be very conscious of at this point onward, is because there is a difference between radians and degrees. You want to make sure you're in the correct angle system when you're doing angles. Okay. It's especially important when you're using a calculator. Okay. Because when we look at the trigonometry in the calculator, your calculator has settings for both radians and degrees. If the problem's in radians, your calculator has to be set to radians. If your problem's in degrees, your calculator should be set to degrees. Okay. Now, the nice thing is that's only going to affect things when we're doing trigonometry problems. Okay. If it's not trigonometry, if it's just regular calculations or regular graphing or anything like that, radians or degrees doesn't matter. Okay. Your calculator, by the way, almost everyone's calculator's default setting is radians. Okay, because again, that's the preferred unit of measurement for angles. Okay, at this level. All right. Any other questions? Get the idea of how this works? All right. Now what we're going to talk about today is the unit circle. Okay. Unit circle and right triangle trig, or right triangles, I should say, on the XY plane. Okay? Alright, so what we're going to start off with is just a quick review of right triangles and how they work. Okay? And then kind of incorporate, show how they involve the unit circle and other things like that. Okay? So first thing I'm going to do is draw a right triangle. Ta-da. How do I know it's right? Because the angle down there is the right angle. Okay. When you have a right triangle like this, okay, you typically go ahead and you label an angle to be the reference angle for the triangle. Okay. We call that angle theta. Theta is a Greek letter. It's the one that's commonly used. It's the symbol that looks like that. Okay. That's a lowercase theta, uppercase theta. Looks like a little, almost like a smiley, like a guy going like that. Sometimes I like to put little eyes on it, because then it looks goofy. Okay. But this is the Greek letter theta. And what it's used for in mathematics is it shows it's the reference angle. Okay. Spelling reference wrong, but whatever. Okay. So it's the reference angle for the triangle. It doesn't matter which angle. Well, it does slightly matters. It can't be the right angle. You don't want to choose the right angle. To be the reference angle, it could be this one down here, it could be this one up here. It just means, though, that when you label the parts of the triangle, it's going to all depend upon that reference angle. Hence why it's the reference angle, yeah.
Does that only work when you're dealing with right triangles?
Yes. Okay, theta is only going to apply to this angle theta. I mean, you could call any, theta is a letter, so I could draw a triangle, call it angle on theta. But as far as what we're going to work with today, okay, and as far as the trigonometry is concerned, it only applies to right triangles. Now, there are methods to apply it to any triangle that we are going to learn, okay? But even so, it's taking this method for right triangles and finding a way to make it work for the other triangles, okay? So it's basically taking the other triangles and redrawing them until they're right triangles. Okay, is what you're actually doing. So theta is a reference angle. So typically when you see this first proposed, this is the angle they choose right there. That's theta. Okay. With reference to theta, each of the three sides of the triangles gets a name. The diagonal side, the one that's across from the 90-degree angle, is always the hypotenuse. That one doesn't change ever. Okay, hypotenuse. Okay, but the other two sides are going to get named specific things based off of where their relationship with theta. The side that makes part of the angle theta, so here's theta, so this side right here, it's actually part of the angle. We call that the adjacent side. And the side that doesn't touch theta, okay, that's on the other side of the triangle from it, we call it the opposite side. Okay? And so you have that's the relationship between theta. Note, if I changed and made this angle up here theta, which I could do, the opposite and adjacent sides flip. This one becomes the adjacent side then. And this one becomes the opposite. Okay?
Was that one more time? The adjacent depends on what with theta?
It's the one it's the side that's touching theta. Okay? That's actually part of the angle theta.
Okay.
So if this is the angle theta, the adjacent is the side that's not the hypotenuse. That's part of theta. And the opposite side is always the side that's not touching theta. So the one that's on the other side of the triangle from theta. Okay? Or opposite of theta, if you think of it in terms of like kind of an old-fashioned way of saying on the other side. It's like that wall there is the wall that's opposite from me. This is the wall that's adjacent to me. And I don't have a wall that serves as my hypotenuse, but you get the idea. Okay? So those are the basic relationships. Now, oftentimes when we take this triangle, we like to inscribe it on the xy plane. Okay? When we do so, okay, we still use the terms, we basically can change, here's theta, okay? This is still my hypotenuse for the time being. We're actually going to give it a different name here soon. But the adjacent side and the opposite side, we can now model using pieces of using the xy plane. In fact, my adjacent side becomes what? What would this distance here be?
1.
Not 1 necessarily, could be 1, but stop that. Okay? But what axis is this? It's the x-axis, right? So if I go in this direction, that's an x length, right? So I call the adjacent side, I call that x, okay? And in fact, from here on out, almost with a lot of times when we do these things, especially when we look at them in terms of x and y, the xy plane, the adjacent side is always going to be modeled as x, the x direction, okay? What then is the opposite side?
Y.
It's y, good. Okay? Because it's the up and down direction. So the length of the adjacent side, in fact, in this case, is going to be x. Whatever x is, okay, that's the length of my adjacent side. And whatever y is, that's the length of my opposite side. And in fact, the point the hypotenuse is pointing to right here, okay, that will have the coordinates x, y. It's your adjacent length and your opposite length encoded in it, okay? And in fact, later on, we're going to find that to be very useful because we're going to look at something called a vector, which is a way of modeling. A vector is different than a function. A function is describing how a curve is built as y changes in relation to x. A vector is going to look at it instead of an angle direction I'm pointing in and for how long I'm going in that direction.
The magnitude.
Okay. The magnitude of it, basically, yes. Okay. And so, but this would be the setup of it all. Okay. So, I guess the takeaway here is when you hear adjacent, think x. When you hear opposite, think y. Okay. So if I talk about the adjacent side, I'm talking about x. If I talk about the opposite side, I'm talking about y. Okay. Hypotenuse is just the hypotenuse. Okay. Any questions there? Okay, good. Now, there are special relationships, okay, within side of a right triangle, okay, that equate the sides of the triangle to the angle, okay. There are special ratios that deal with this, and they're basically called. There's 6 of them actually, and these ratios end up being what a lot of trigonometry is all about, okay. I'll just go ahead, and it's just relationships between the sides and the angle theta, okay? And so there's 6 of them, so there's 6 trigonometric ratios. Okay? The first one is called the sine, okay? And the sine is abbreviated S-I-N. Don't say sin, say sine. It really annoys me to know when people are like, sin theta. No, sine of theta. Okay, so the sine of theta, and that's equal to the ratio of the opposite side to the hypotenuse. So it's y divided by h, okay? Alright, so if I do this thing called the sine to the angle theta, it's equal to the opposite side divided by the hypotenuse side, okay? And so it's a way then to equate the sides of the triangle to the angle, okay? Or vice versa, the angle to the sides, okay? So that's the first one, the sine. The next one's called the cosine. That's abbreviated C-O-S. Don't say cos, say cosine. If you say cos, I will yell at you. Okay? I won't actually yell at you. I will fuss at you, though. And if you keep doing it, I'll throw an eraser at you. The next one.
Wait, it was equal to what? That's
Oh, sorry, x over h. So in this case, it's the cosine. Excuse me. I should, instead of going on rants about sine and cosine, I should actually explain what they are. The cosine is same thing as the sine, except it deals with the adjacent and the hypotenuse, as opposed to the opposite and the hypotenuse. Okay, so it equates those two things together. Okay, and again, it's this thing I could do to the angle theta. I could do this thing called the cosine to theta, and it just happens to be equal to x over h. Okay, the length of the adjacent over the length of the hypotenuse. Okay, the third one is called the tangent, abbreviated T-A-N, theta. Again, don't say tan. It's tangent. And the tangent of theta is represented as, again, it's a ratio. In this case, it's the opposite side to the adjacent side. So it's y divided by x. Okay? Okay. These are the main 3. You call these the big 3. Okay? They're not the only ones. Okay? There are actually 3 other ones, and the other 3 are actually the inversions, not the inverse, because the inverse is different, trust me. This is where things get kind of confusing with inverse. Okay? But they're basically all of these guys flipped upside down. Okay? So the first one's called the cosecant, abbreviated CSC, okay? And it's the flip of the sign, so it's h over y, okay? The next one's the secant, abbreviated SEC, great football. And that one's the flip of the cosine, so it's h over x. And the last one is the cotangent. What do you think the cotangent is? The flip of the? Yes.
X over y.
Yeah, it's x over y. Okay.
Is that cot?
Cotangent.
Oh.
Again, don't say it as cotangent. Don't say cot. Cot theta. People say that. It's so like. Okay. Sine, cosine, tangent, cosecant, secant, and cotangent, okay? And that's what they're all equal to, okay? How these things are used, to give you an example, okay? Let's do one that actually trying to think of a good one I know the answer to. Yeah, this one should work out fine. Okay. Let's say I had a triangle. Okay. Like so. Actually, I should do this.
No, it's a theta.
Okay. I should do this on the boards. Camera can catch me with it. Okay. Show you an example of these things in action. Okay. Let's say I had a random right triangle. Okay. And I knew the hypotenuse of this right triangle was 12 in length. And I knew the angle theta that it made in relation was 56 degrees. Okay. I wanted to find how long each of these sides were. Okay. What I would do is I would just set them up using these ratios. I would say this. I would say to find y. I would say the sine of 56 degrees is equal to whatever y was over 12. And that's a ratio, right? And I should just be able to easily solve for y there. Okay. And cross multiply here. I would get 12 sine of 56 is equal to y. If I wanted to find x, I'd do the same thing. Okay. My setup would be it's x over h this time, so I'm going to use the cosine. So I would say the cosine, 1 second, of 56 degrees is equal to x over 12. So x is equal to 12 cosine of 56 degrees. I would pop those in the calculator and get my answer. Okay. You have a question?
Yeah, if you change the angle that you use for theta, do the ratios change as well?
The ratios would flip. Okay? So basically, if I made this one up here, my angle theta instead, let's see, that's going to be a what, a 34-degree angle? Yeah. Okay? If I made that my angle theta instead, then I would, x and y would flip positions, basically. And so this side here would be found by doing 12 cosine of 34, and this one would be found doing 12 sine 34.
That's not
Okay.
adjacent.
Because the opposite and adjacent would flip. So what would happen there is, if I use this one, I'll go ahead and change the colors.
The
on it.
opposite and the adjacent just to flip the
Yeah.
ratios.
That would
down.
become x. That would become y. Sine cosine still remains sine cosine. Okay.
Okay,
You
that
just
makes
use a different angle. Yeah.
Do you have a trick to remember when cosine is applied and when sine is applied?
Okay. Basically, besides just remembering
Yeah.
what the ratios are, which you do have to know, by the way, and there is a mnemonic for it.
No,
Okay?
yeah.
There's several. One that's used is
What's your favorite?
my favorite's a little PG-13. It's one student taught me at my old school. It's some old hooker caught another hooker taking Oscar away. Okay? Some old hooker, sine opposite hypotenuse, caught another hooker, cosine adjacent over hypotenuse, taking Oscar away. Tangent opposite hypotenuse.
Thank you.
Or, sorry, adjacent. That's one. Another one you'll hear is a variation on that. Some old horse caught another horse taking it away. It's a PG version of it, of the one I just did. Another one is it's the Native American chief Sokotoa. Because if you wrote out what Sokotoa is, it writes out. Whoops. Sorry.
What's a Sokotoa?
So, Toa. It's basically it's a Native American chief named Sokotoa.
Sick. Okay. That's cool.
Represents all. So chief. So some people remember it as Chief Sokotoa. Yeah. And you get them. Those are all mnemonics from it. You know, to be honest with you, it's only 6 things you have to actually memorize.
Yeah, it's not hard.
So it's
I mean,
really
that's-
not that
Yeah.
hard. And the thing is too, it actually gets even easier because what we're doing right now is we're doing all this in regard for any triangle, okay? But it turns out I can make life a lot easier, okay, by taking these things and applying them to right triangles inscribed on the xy plane, okay? And I can turn those triangles in the xy plane into unit circles. And when I do that, okay, all this trigonometry becomes a lot easier, okay? There's a lot less you have to remember, okay? Why do you think that would be the case? What happens to the hypotenuse of each of these triangles if I turn them into unit circles?
becomes the diameter.
Oh, okay, so not diameter, but what's the other thing?
Radius.
The radius.
Yeah, the radius.
And the whole idea behind a unit circle is that the radius is how long?
Half the.
No, it's constant, right?
Pi.
Oh,
It's not pi, it's,
Which one's X and which one's
constant.
Y?
remember from yesterday, a unit circle has a radius of how many radians in length?
One.
One.
Oh, yeah.
One radius in length, right?
Yeah.
So your hypotenuse becomes 1,
Okay, got it.
okay? And becomes a fixed quantity, and then the rest of everything else falls into play.
Oh, sick.
Let's take a look at that in 1 second. But going back to this right here, okay? This point, you would get out a calculator and you would just plug those in. Some of these you can calculate by hand, you don't need a calculator for, but it requires knowing, requires memorizing bits and what these values are. And I'll have you do have to do that for certain ones. Luckily, 56 degrees is not one you have to remember. Okay. First thing I want to do is make sure my calculator is set to degrees. Mine is set currently to radians. How I figure out how to change it, there's a button on your calculator that says mode. You click on that, brings up this menu, lots of different things. The third one down says radian. Flip it over to degree, hit enter, the calculator is now in degrees. On your calculator, I have no idea how it
Yeah,
works.
it's here.
Same idea?
Yeah,
Okay.
it's shift setup.
So, calculator's now in degrees, and you just enter that in exactly as it appears. 12, sine is right there. Okay, sine of 56. Hit enter, the answer is 9.948. So, yeah. So y then is approximately equal to 9.948 units in length.
Yeah.
And the cosine, I can either use the Pythagorean theorem at this point to find it, or, since I've actually got this calculator already set up for it, let's just do it with the cosine. And it's approximately equal to 6.71.
Is
0.
is graph not something we have to like?
A gradient? No,
Yeah.
don't worry about gradients.
Ah, okay, cool.
Okay.
How do you change it into?
So in most calculators, let's see, on yours, what you would do here, you hit the mode button, and right down there it says radian, degree, you would just switch over, yep, okay. Anyway,
Sorry.
yeah, gradients are like fancy notation that engineers use, because they have to be special. That I don't even think most engineers use even, but I just know it doesn't really
Okay, apply
Yeah.
that. Yeah.
do anything. Okay? So, but that's basically how these things are set up. Okay? Any questions so far? Okay, good. Now, I could have also, too, I didn't necessarily have to use the sine or cosine. I could have also used to solve this the other ones, the cosecant and the secant. Because remember, the cosecant of theta is equal to h over y. So I could have set this thing up as the cosecant of 56 degrees equals 12 over y, and then solve for y, in which case I would get y is equal to 12 divided by the cosecant of 56 degrees. There's a problem with cosecant though, okay? And secant and cotangent. Look at your calculators. Is there a button for secant, cosecant, or cotangent on there? No.
Arcs.
There's sine, cosine, and tangent, but there's not secant, cosecant, or cotangent. You say, oh, well, what about maybe I could just use second and use sine negative first, cosine negative first, tangent negative first. Actually, you can't. Those represent something different, something called the inverse sine, the inverse cosine, the inverse tangent, which are not the same thing as the secant, cosecant, and cotangent. Okay? In fact, another name for those is the arc sine, another name for that second above the sine is arc sine. Okay? And what it does is it's the thing that undoes the sine. Okay, and we're going to see that later on this month. It undoes the sine, basically meaning if I need to solve what the angle was, I could do so. Okay, because I could say sine of theta equals 9.948 over 12, then use the arc sine to undo it on both sides. That gives me theta is equal to arc sine, all that stuff, and I solve. Okay. Turns out your calculator does not have the ability, most people's calculators don't have the ability to do secant, cosecant, or cotangent. How you do, if you do need to calculate that in your calculator, you do it as 1 divided by the sine, or 1 divided by the cosine, or 1 divided by the tangent, okay? So, a way to remember those, okay, is that, remember, the cosecant is the flip of the sine, it flips the sine on its head, so I can write that the cosecant of theta is equal to 1 over the sine of theta. And so that's how I would enter it into a calculator, 1 divided by sine of theta. Okay? Excuse me. Secant of theta is 1 over the cosine of theta, and the cotangent of theta is 1 over the tangent of theta. Okay? Likewise, okay, the sine of theta could be written as 1 over the cosecant of theta. Okay? The cosine of theta could be written as 1 over the secant of theta, and the tangent of theta could be written as 1 over the cotangent of theta. Okay? This is the relationship between trig functions. Okay? And if you're wondering, well, how do I know this is absolutely true? Again, the sine, remember, is basically the sine is y over h. That's what it's equal to. The sine of theta is y over h. So cosecant of theta is h over y, so I can replace that with h over y is equal to 1 over y over h. Well, it's 1 over y over h over y. Okay, it comes out to be the same way. Okay, so that's sort of the relationship between those 6 right there. Any questions? Okay, now that we've got all this in place here, what we can do with all this is generate something called the unit circle. Okay, and the unit circle is basically a method used to know. Okay. Okay. The unit circle is a way to basically take all this idea and make it as simplified as possible, and then it corresponds to actual xy values that you can use to calculate things by hand. Okay. The idea behind the unit circle is that it's a circle whose radius is 1 unit in length. Okay. Basically, the unit circle has a radius of 1 radius. Okay. The idea is I can inscribe, though, in my unit circle, a right triangle, just like I've done right there. Okay? There's my right triangle in there. Okay? The hypotenuse of this right triangle is the radius of the unit circle. Okay? So I've got a radius here, and it's equal to 1. Okay? Notice how my adjacent and opposite sides still remain x and y, don't they? So this is still the side x, and this is still the side y. Okay? That means now, when I write this, that means now when I do my trigonometric functions, I can just write them in terms directly of x and y. I don't have to bother with y over h or x over h, because what's h always going to be now? 1, because it's the radius. Okay? So I can say that the sine of theta is just equal to y, and the cosine of theta is just equal to x. The tangent of theta is still y over x. Then the rest of them come out the same way. So cosecant is 1 over y. Secant is 1 over x. And finally, cotangent my brain is not working today. Is x over y. Okay. So there you have it. Okay. Any questions there?
So you literally just take the triangle and you just put it in there, and then what? You just keep all you keep is the angle measure, right?
Yep. Angle measure, and then the angle measure. So if I did, like the sine of like pi over 6, the answer I get for that is y. Is the distance of y. Okay. If I did the same with cosine, I get the x distance. Okay. But that's also telling me, okay, whatever my radius, whatever theta is, whatever it's, remember theta, it tells me where the radius of the circle is pointing to, what the xy location of that is. Okay? And in fact, there's lots of known xy locations that correspond to known values of theta, okay? So for example, if theta is 0, my x distance is 1 and my y distance is 0, okay? Because what's happening, my radius is sitting right on the x-axis. I'm all radius and no, I'm all adjacent, no opposite, basically, okay? So this is at 0 dash 2 pi, or 0 or 360 if you want to think of it that way, okay? Up here, at pi over 2, or 90 degrees, okay, I have at the coordinates 0x, 1y. So a right angle, okay, is pointing straight up and down, so the x value of a right angle is 0, the y value is 1, okay? Over here at this location right here, this would be pi or 180 degrees. Well, my coordinates are going to be -1, 0 there, okay? Again, because I'm now, my radius is pointing in the negative direction, going negative x, okay? Down here, same idea. This is the location, remember, 3 pi over 2, or 270 degrees, okay? I'd have the xy coordinates of 0, -1, okay? So, sort of the 4 cardinal directions are easy. There are some combination of 1, 0, or 0, 1, okay? And that's what they correspond to. Turns out, and we're running out of time, we're not going to be able to hit this all today, but that's okay, we'll do it tomorrow as well, we'll work on it some more. Some of the homework might be required if that's whatever. Okay. There's actually a picture of it all in your book, by the way, too. I'll tell you the page here in a second. Okay. What we could do, though, with known special right triangles, if you remember those from geometry, like the 3, 4, 5 triangle. Actually, not 3, 4, 5, that's a bad one. But something like a 30, 60, 90 triangle. We know how to work that one, right? Or the 45, 45, 90 triangle. We know the ratio of those sides of those triangles, right? Well, we can go in and apply them to a unit circle and be able to actually fill in a bunch of locations around the unit circle, okay? And if you could do that, you've got basically the ability to calculate things like the sine, cosine, and tangent by hand, okay? Which is very useful to do, okay? For a full picture of the unit circle with all the known locations, or all the good locations on it.
It's up in the start of
Is it in the very start of the book?
yeah.
So it is. If you open up your book, the very inside cover, right there is a full unit circle with every location that you need to know on it. Okay?
So that's the Saturday test.
Basically, yes. The quiz that's on the quiz,
That's wait, sorry.
I'm going to give you in the morning on Saturday. It's just regurgitate me this.
So if we know that, we're good.
You're good. You're perfect.
What page is that?
It's in the basically the cover of the book.
Alright,
Okay.
I'll have that.
So,
You just need to go to know the degrees and the radians.
yep, and the location values. Okay. So, for example, if I ask at 45 degrees, what's the radial measure? It's pi over 4. And what's the coordinates there? It's root 2 over 2. Root 2 over 2. The thing is, it seems like it's a lot to memorize, except it's the same numbers for across the entire thing. Okay? And what I'm going to do with you tomorrow is teach you how to quickly figure out where locations are in the circle. Because there are many, many different methods
That's all.
to remember them, or find them if you can't remember them. Okay?
This thing